All right, good morning. Today we're going to get started with our first day of notes, and the very first thing that we're going to be covering are the properties of exponents. Now, most of you have probably seen some of this, but for many of you it might actually be new material. A lot of times this is covered in those last months of your 8th grade year, and given the fact that we were all on our stay-at-home order, you might not have covered this. So today we're going to be covering the product and the power rule, and then tomorrow you're going to be covering the quotient rule, the negative exponent rule, and the zero power rule. But today we're just going to be working on the product and the power rule. Every day we ask that when you watch these notes videos, you take notes by paper and pencil in a spiral notebook. That's going to help you to retain the information. Often watching a video is not enough. There's a lot of research that shows that when you actually are writing it down, you're going to retain it a lot more. So if you could do that for us, that would be awesome. As I work through the different rules, I'm going to be sharing the rule, and then I'm going to be talking about the why. Why does it work? In math, there are a lot of different rules, but at the end of the day, I think about it myself. I don't always remember the specifics of a rule, but if I know why it worked and the foundational information that the rule is based on, then I can always break it down. And it doesn't matter if I remember the rule or not, because I'm able to start with the basics and work from there. So we will go over the why all of the time. All right, so the first rule we could call, or that we're going to talk about, is what's called the product rule. In the product rule, you have two exponential expressions that you're multiplying together, and they have the same base. So if you take a look in this situation, I have a to the x power times a to the y power, right? So they have the same base. A is the base. The exponent, in this case, is the x and the y. Now, the rule in such a case is if the bases are the same, let's change this. If you multiply two things with the same base, you keep the base, and add the exponents. All right, now I'm going to bring you to the section where I'm going to give you an example where we have x to the second power times x to the fourth, and we're going to talk about why this works. So I want you to think for a moment about what x squared actually means. Now, if you recall, an exponent shows us repeated multiplication. So x squared means x times x. Now, x to the fourth, that means x times x times x times x. So if we sort of decompose the expression into what we're actually multiplying together, we end up with this expression here. Now, if we go to put it back together, right, and to simplify it, we have an x, and since you're multiplying it by itself 6 times, that would be raised to the 6th power. So that's why the rule works, is if you were to actually decompose the expression out and then put it back together, you would find that in each case, everything that has the same base, you're actually adding the exponents to get the simplified expression. Now, if you just kind of preview the 3 examples I have here for the power or for the product rule, you're going to see they're a little bit more complex. Well, in number 2 and number 3, for example, there are coefficients. Coefficients are the numbers in front of the variables. So we need to talk about how to deal with those. So if you take a look at the steps, it says we're first going to multiply any coefficients if needed, and then we're going to add the exponents of the variables that are the same. So let's take a look at our first example. We have y to the third times y to the fourth times y to the fifth. Well, in this case, there's only one common variable. That variable is y. And if we add up all of the exponents on it, 3 plus 4 is 7, 7 plus 5 is 12. So this would be y to the 12th power. Now, if you were to actually break all of that down, right, think about this. Y cubed would be 3 y's. Y to the fourth would be 4 of them. y to the 5th would be 5 of them. And so that's why you end up with the y to the 12th in the end. All right, if you take a look at number 2, copy down the example problem, please. We have the quantity of negative 1/3 x to the 3rd y squared times the quantity of 12 x y to the 5th. So if you notice, we have coefficients. We're going to go ahead and multiply those. So negative 1/3 times 12 would give you negative 4. And in this case, there's two different variables. We have x's, and then we have the y's. So we're going to first deal with the x's. If you take x cubed times x, you would keep that base, and you're going to add the exponents. Now, in this case, this x is by itself, so that means it has an exponent of 1 on it. So that would give you x to the 4th, and then y squared times y to the 5th. That's 2y's and 5y's, so that's going to be 7 total. So you end up with negative 4, x to the 4th, y to the 7th power. All right, number 3. I'm going to have you guys try this one on your own. Let's see if you can do it. So first identify what pieces you can multiply. I'm going to tag these with different colors here. And then we'll go ahead and multiply them. So 2/5 times negative 4 is going to give us negative 8/5. A to the 2nd times a, just a to the 1st, it's by itself, would be a to the 3rd. Then you have an x and an x squared, so that's x to the 1st times x squared, which would be x cubed. And then y to the 4th times y to the 3rd is y to the 7th. Now, most of the time you're going to see it left like this, but I want to point out that you could also write this one as negative 8 a cubed x cubed y to the 7th all over 5. These two actually mean the same thing. So just kind of custom on how you're used to writing things. If you had, this one, you would be correct. If you had this one, it would be correct as well. All right, now we're gonna go to number 4, and this is one that I always say is a conceptual problem, because if you noticed, one of our exponents is a variable. Rules don't change, right? So the rule is the same. If you think about what our rule had been, it said if two things have the same base, you keep the base, which in this case is a, and you would add the exponents. So in this case, even though it's a little bit more abstract, we would actually keep that as 3 plus x. So you get a to the 3 plus x power. All right, the next rule we are going to dive into is the power rule. The power rule happens in one of 3 cases. It's basically when you have a quantity and you're taking it to another power. So in case A, we have a to the x power and you're raising it to the y power. In that case, if you notice, you're keeping the base and you're multiplying the exponents together. So you keep the base and you multiply the exponents. Now, let's go underneath the section where it says, why does it work? And notice I have a squared to the 2nd. Well, let's break down the outer exponent and what that means. If we have that outer exponent, it means that we have 3 squared times 3 squared. Well then, if you break down each of those, the first 3 squared is 3 times 3, and the second 3 squared is 3 times 3. Well now, if you put it back together to simplify it, that's 3 to the 4th power. So notice you're keeping the base and you're multiplying the exponents in this case. Now, the second place you'll see this is like letter B here. Right? In letter B, you have the quantity of a times b to the x power. And that's going to give you a to the x and b to the x. Notice that the rule is actually still the same. You're still keeping the base and you're multiplying the exponents. It's almost like you're distributing this x to the exponents. Now in this case, the exponent on the a and the b would both be 1. So a to the first raised to the x would be a to the x. B to the first raised to the x would be b to the x again. All right, now let's take a look at this example in letter B here, right? 2 times 3 to the third. Well, if we were to break that out, right, this means that we have 2 to the third times 3 to the third, which is exactly what this rule would end up saying. Now, if you wanted to prove that mathematically, right, we know that 2 to the third is 2 times 2 times 2, so that's 8. 3 to the third is 3 times 3 times 3, which is 27. And then if you take 8 times 27, that gives you 216. Now, because you guys are so savvy, you know your order of operations already. And if you started back with that original expression of 2 times 3 to the third, most of you would probably say, oh, I have to do 2 times 3 first, right? And 2 times 3 is 6, and that would give me 6 to the third. Well, guess what 6 to the third power is? It's 216. So that's why that rule ends up working. It ends up giving you the same solution. All right, and the last place that you're going to see the power rule is in this scenario, where you have a over b raised to the x power. That would give you a to the x power over b to the x power. Now, if you notice, there's this tagline on the end where it says where b cannot equal 0. We have to specify that in this case because if you notice, in our denominator we have the letter b. If you think back, what happens if you have a 0 in the denominator, right? That's an undefined situation. It can't exist. You can't take a number and divide it into 0 groups. So that's why it doesn't exist, and that's why you will often see these little restrictions written here. It's just kind of don't worry about them. It's information that we need to say mathematically so that we're correct. But that just tells us that, the 0 can't exist. Now, in this case, again, you're basically taking that exponent of 3 and you're distributing it to the exponents in the numerator and denominator. So this would give you 3 to the third over 5 to the third. Well, 3 to the third is 27, and 5 to the third is 125. And if you were to take this, get your decimal number, if I take 27 and divide by 125, that gives me 1.944 approximately. Well, then let's say I take 3/5, right? 3/5 is 0.6, and if I take 0.6 to the third power, guess what I get? I should get the same exact thing. Did I get that? Let me just double check my math here. Sorry, this is not correct right here. 1.944. That can't be correct because the numerator is smaller. So this actually gives us 0.216. And if you do the 0.6 to the third, that's also 0.216. So again, you get the same thing. So that's the why. Why does it work? All right. Our set of examples here are going to explore the power rule. And there's a number of different examples. And if you notice, kind of just perusing them initially, the parentheses exist in different parts of the problem. So we're going to kind of dive in and see what each one holds for us. All right, so example 1, we have x to the third raised to the third. So we know it's the power rule because you have this outer exponent outside of a set of parentheses. You're going to keep the base, which is x, and you're going to multiply the exponents. So 3 times 3 will give you 9. So this is x to the 9th power. Now, again, if when you look at these problems, you are doubting yourself, go back to the basics, right? If we know that we have x cubed to the third power, that means x cubed times x cubed times x cubed. Each of those would give you 3 x's, and then when you put them back together, it would give you the x to the 9th. All right, number 2. You have the quantity of 4xy squared raised to the second power. So because we have that parentheses and that exponent of 2 outside of it, that means everything inside it needs to be raised to the second power. So you're going to keep the base, multiply the exponents in all cases. So this would give you 4 to the second power, because the 4 initially had an exponent of 1 if there's nothing there. So 1 times 2 is 2. X would also be to the second, and y would then be to the fourth, because 2 times 2 would be 4. Now in this case, we have this 4 squared. Most of the time you don't leave your answer like this. You actually figure out what 4 squared is, because that's numerical. So this is 16 x squared y to the 4th power. Most of the time, we actually say to evaluate your coefficient through the power of 5. So meaning if the exponent is 5 or smaller, actually figure out what that number and that coefficient is going to end up being. All right, let's take a look at number 3. Number 3, you have 5 times the quantity of mn to the 3rd power. Now think about what is actually being raised to the 3rd power. Is the 5 included in that? Now, hopefully you're recognizing that 5 is not in the parentheses. So in this case, the 5 would just come down, but you would raise both the m and the n to the 3rd power because they are in the parentheses. So you would have 5 m to the 3rd and n to the 3rd. So sort of a little trick question, just to kind of get you recognizing that the placement of those parentheses actually makes a pretty big difference on what your answer is going to be. All right, number 5. If you look at number 5, we're combining rules here. We're going to combine the product and the power. So if you take a look at the first set of parentheses, you have 6x to the second, y cubed, and you're raising it to the 2nd power. Each thing in each little part of that term has to be raised to the 2nd power. So you would have 6 to the 2nd power, which if you think about it and you want to simplify as you go ahead and do that because it'll make it easier for you, right? What's 6 squared? 6 squared is 36. Then you have x to the 2nd raised to the 2nd. That would be x to the 4th. Y to the 3rd raised to the 2nd would be y to the 6th. Now, with your second set of parentheses here, you have x, y, z, and notice that there's no exponent outside of that. So that just means you're going to take what you just got and you're going to multiply it by x, y, and z. Now, this should be familiar. These are just like the problems you just did in the previous section of our notes today. So you're going to multiply any coefficients you have. In this case, we just have the 36, so we'll bring that down. And then you use the product rule on any of your like variables. So we have x's and we have y's. So we're going to keep the base and we will add the exponents on those. So x to the 4th times x to the, this would be to the 1st, is x to the 5th power. Then y to the 6th, and this would again be y to the 1st, would give you y to the 7th. And then notice you have that lonely little z there, so you'll just bring that into your answer. So you end up with 36, x to the 5th, y to the 7th, and z. All right, number 6, there's a lot of negatives here. Now, I put the negatives here because I want us to recognize what they mean in each of these cases. Now, the negative out front is like a -1. If you take a look at the second part of the problem, we have 3m cubed n squared all raised to the 4th power. Because that exponent is outside, you're going to raise everything in those parentheses to the 4th. Now notice that -1 that was out front, you're not raising to the 4th power because it was not in the parentheses. So then we have 3 to the 4th power, which 3 to the 4th power is 81. Then m to the 3rd raised to the 4th would be m to the 12th. n squared raised to the 4th is n to the 8th. Now, this next part is tricky, or at least I think it's tricky. This is where students sometimes make mistakes. Now, you have a negative sitting there in front of the n squared. Notice that it's just in front of it. So that really means to us that this is a negative 1 n squared, and you're raising that to the 5th. It's good to separate the negative off of that variable and treat it as a coefficient of negative 1 versus trying to treat it as a negative n. So now when you do this and you use your power rule, you're going to take negative 1 to the 5th power, which negative 1 to the 5th power is a negative 1, and then n squared raised to the 5th is n to the 10th. Oops, I don't like the way that looks. Now you can go ahead and use your product rule from before. So find all your coefficients, those are your numbers, and then go through and find all the like variables. So here we only have the m, that's the one m, but then we have the two different n's. So negative 1 times 81 is negative 81. Negative 81 times negative 1 is a positive 81. The m is by itself, so we'll bring that down. And then n to the 8th times n to the 10th, that's 8 n's and 10 n's, so that's going to be 18 of them. All right, let's go to number 7. All right, take a moment to copy the problem down. You have the quantity of 1/2 m to the 4th power, n to the 5th power, all raised to the 2nd power. And then you have the quantity of 4xn cubed raised to the 2nd. All right. Again, this is a combination of the two rules that we've learned today. So in the first scenario, you're going to take everything to the 2nd, and then you'll take everything to the 2nd in the second set of parentheses as well. Now, 1/2 to the 2nd power. If you take 1/2 times 1/2, you're going to get a 4th. Then you have m to the 4th raised to the 2nd is going to be m to the 8th, because remember the rule is to keep the base and multiply the exponents. And then n to the 5th raised to the 2nd is n to the 10th. Then with our second set of parentheses, you'll have 4 to the 2nd, which is 16. And then you'll have x, which in this case is again to the 1st, and then you raise that to the 2nd, so that's x squared. And then you'll have n to the 6th. And now kind of identify what you have. You have your coefficients. We have an m. That one's all by itself. Then we have an n and another n. And then we have this x by itself. So 1/4 times 16 is 4. The m to the 8th is by itself. We'll bring that down. Then you have the n to the 10th times n to the 6th. That's n to the 16th. And then that x squared was also a loner, so you'll just bring that down. All right, we're going to take a look at number 8. I'd like you to kind of try this one on your own. So you have the quantity of negative 3 rs raised to the 2nd times the quantity of negative st cubed raised to the 3rd. When you raise everything to the 2nd power in the first set of parentheses, you should have gotten 9 r squared s squared. The second set of parentheses, it's helpful to look at that as a negative 1 st to the 3rd raised to the 3rd. And then when you raise everything to the 3rd power there, you would get a negative 1 s cubed t to the 9th. And then identifying your coefficients and your like variables. you'll be able to take your 9 times negative 1, which would give you a negative 9. The r variable is by itself, so you'll just bring that down as r squared. You have two different s's that you're going to multiply, so s squared times s to the third will give you s to the fifth, because there's 2 of them and 3 of them. And then the t is a loner, so you'll bring that down. All right, our last 2 problems are conceptual problems. So again, these are very similar to that one we did in the product rule section. They're a little bit more abstract because you have a variable in there. But again, just keep to the rule. What does the rule tell us to do? So in the first one, we have 7x to the p power, and that is all raised to the second. So everything inside those parentheses needs to be raised to the second power. So 7 to the second is 7 times 7, or 49. And then when you take x to the p raised to the second, remember you keep the base and you multiply the exponents. So p times 2 is 2p. All right, number 10 is conceptual again, but we are combining both rules. So take a moment to copy it down. You have the quantity of x to the fourth raised to the c power times the quantity of x to the 3c raised to the second. So in the first scenario, you'll have x to the 4 times c, or 4c. In the second scenario, you keep the base, which is x. When you multiply your exponents, 3c times 2 is 6c. Notice at this point you have 2 terms that have the same base. When they have the same base, we keep the base, and you're going to add those 2 exponents together. So 4c plus 6c is 10c. All right, you have finished your first day of notes. You might need to go back and rewatch parts of this, but the best thing is that hopefully you have written them down in your spiral notebook. You might want to get up, take a stretch break, and then log back on to Google Classroom, and you're going to find an assignment in there. We ask that you complete the assignment by 11 a.m. and then join us again at 11:30 a.m. in our Google Meets. At that time, we're going to go over any questions you have, and I'm actually going to look at your work prior to our meeting, so I can kind of go over things that I think might need some review. And we're probably going to do a few practice problems together, and then we'll preview what you're going to be doing tomorrow. All right, so we're going to see you face-to-face again on Google Meets at 11:30. Again, please submit your work by 11. All right, see you in a bit.